All right, let's make a start. This will be a fairly quick lecture section, especially if no one else joins. It'll just be there basically to get it down on recording that we've done it, so we can have a review on that, and then we'll move into breakout room questions, or potentially just stick in the main room, depending on who joins. So, limits and continuity. This will be a bit of revision of it. So first, what is a limit? So limits, you're basically looking at what happens to the y values of a function as you get closer and closer to some determined x value. Like, for instance, if you wanted to find the limit as x approaches 0 on this graph, basically what you do is you look at the y values immediately from the left and watch the trend line, and you look from the right and also watch the trend line. Whatever they get closer and closer to is referred to as the limit of that function for that particular x value. So this would specifically be the limit as x approaches 0 of x squared. That's how you would describe that. A limit can only exist if as approached from the left is the same thing as approached from the right. Obviously these both approach the exact same value, so you would consider the limit to exist, and its value would be 0 because it reaches y equals 0. Whereas a function like this, if you come from the right-hand side, you shoot to positive infinity. If you come from the left-hand side, you shoot to negative infinity. Two separate values. Technically, neither of them are even values to begin with. Infinity isn't considered a number or a value. Basically, limit does not exist. It's diverging away. Oddly enough, this is the kind of situation where you would actually care to use limits versus just knowing what the y value is at that spot, because limits are best used for exploring what happens to a function in a discontinuity, right? So this x equals 0 would be discontinuous for a hyperbola. If you sub in x equals 0, we don't know what happens. In particular, this is an asymptote, right? And so limits are basically the exploration into figuring out what's likely to have happen. This is basically whatever. You can use these if you want, although as far as method is concerned, basically none of them are particularly helpful. You can pretty much always just look at your function from the left, from the right, and observe, or you can, as you'll see in the next section, you could just sub the value directly in after doing a bit of rearranging. So, one of the first types of questions that come up is this idea of a discrete limit, which we kind of just saw. We saw limits as approaching x equals 0. This one is described as approaching x equals 2. Now, again, as I sort of said, limits are best used for cases where you have discontinuities. In this case, if you were to just directly sub in x equals 2, well, firstly, it tells you can't, but second, even if you did, you get a divide by 0 error. So the way you handle this is through factorization. Pretty much every single circumstance like this is going to be handled via factorization. Simply factorize your numerator. You'll realize that the denominator will cancel out in some way, shape, or form. From there, you'll observe that it will actually be easy enough to sub in that x equals 2 value. Now, worth pointing out, the value of the limit as x approaches 2 is equal to 3. The limit is 3, but f of 2, so if you were just to sub in x equals 2, you have to give the number or the result undefined. Limit does not always equal value. Limit is 3, function is undefined. If you were to define this function in the CAS and try to sub in x equals 2, it would tell you undefined. That's discrete limits. The last thing you look at are when limits go to infinity. So there's a few shortcuts for each of the different cases that come up, although technically speaking, it's the exact same approach for any set of polynomials divided by each other. These shortcuts are there just so you can have an immediate answer. Like, for instance, the top and bottom shortcut is pretty much just you have this answer literally always. The second dot point, you have to do a slight bit of math, but still faster than if you had to do it directly from pure algebra. We'll have a look at the approach overall, and then we'll look at where the shortcuts come from. So, this basically means the degree, so the highest power of your polynomial. P of x, in fact, let me remind myself. P of x is your numerator, Q of x is your denominator. So basically, if the numerator has a smaller degree than that of the denominator, so linear, quadratic, this is always going to go to 0. The reason why is because any of these limits can be solved first by dividing the top and bottom of your fraction by whatever the highest order or degree term is. So in this case, you see the highest degree term is going to be x squared, so you divide the top and bottom of your fraction by x squared. Now I've used negative indexes, so I'm multiplying instead of dividing, but it's the exact same procedure. When you do that, you're going to create a whole bunch of things that have x in the denominator. The advantage there is because when you sub infinity into those spots, having an infinitely big denominator means that term effectively goes to 0. Right? Like if you think about like a half into a quarter, into an eighth, into a 16th, as the denominator gets larger, the value gets smaller and smaller and smaller as it gets closer and closer to 0. Right? So an infinitely big denominator means the entire thing effectively disappears, leaving you with, well, final results of 0. But I think more importantly, basically the only term that gets to still exist is whatever the biggest term was. So you'll notice that the x squared, when all is said and done, is the only thing that gets to have its coefficient. Everything else disappears. That's why when your numerator is smaller than your denominator, your result will always be 0, because the biggest term is down here. Right? There's nothing else, everything else will disappear. So the shortcut, as soon as you observe that, you just write 0. If you want to do some arithmetic, if it's like a 2 marker maybe, you might want to put some of this down, but I'd be shocked if anything like this was a 2 marker. When they have the same degree on top and bottom, so both of these have x cubed, again you're going to see the exact same thing, which is the x cubes are the only thing that keeps their coefficient. And so basically your final result will always be the ratio of those two coefficients. Here's your 4x cubed, here's your 1x cubed, 4 divided by 1, 4. So it's a nice and easy shortcut for you to follow. The only thing that gets to still exist in the function is whatever the biggest term is in that function. If there's two of the same highest order term, they both get to keep it. And then lastly, if your numerator is bigger than your denominator, again, as we said, biggest term is the only thing that gets to keep a coefficient, which means your entire bottom disappears down to 0, which for our purposes we consider as undefined. The only reason why I've put a negative infinity there is because that's what the CAS will give you. You should still write undefined, and if you really wanted to, you could put negative infinity there as well, just to sort of cover your bases. But the mathematically accurate answer there is to say undefined. Yeah, that's all limits. Anything in there worth revising in any more detail?
I think it's all good.
It's all good? Nice. Last up, continuity. Cool. So observing continuity is a pretty easy thing. You literally just look for white circles and spots where there's gaps in the function, right? As far as putting into words what's precisely wrong with the function, that's the thing that requires a bit of memorization, because you have to sort of refer to one of those 3 criteria well, maybe one or more actually, because more could be more than one reason why a thing is discontinuous. First things first, must be defined at a point. So that's pretty easy, right? If you do a vertical line for a particular x value, is there a dark circle equivalent? Like this function, for instance, is fully defined over this entire domain because any vertical slither that you draw has at least a single dark spot on it for the function. If it lacks one of those, then you say it's this criteria that's not missed. Function is not defined at x equals whatever it is on the graph. In fact, probably a better picture would be, yeah, let's just play one of these. So like, for instance here, the vertical line on this one at x equals 3, there is no dark spot that exists on the graph, whereas for x equals 4, there is. It's up here. So this one's discontinuous at x equals 3 because of that first criteria. This x equals 4 is also discontinuous, but for a different reason. it's discontinuous because the limit does not exist at that point. And so essentially what's happening there is if you look at your vertical line x equals 4, coming from the right-hand side, you reach whatever this y value is. Coming from the left-hand side, you reach whatever this y value is. Two separate spots, the limit does not exist. And so for that reason, anytime you have this big gap between your values, it's that second criteria, the limit not existing, that you would point to. Then the last one, which is fairly niche for it to be the only reason for a function to be discontinuous, is that both the value of the function and the limit need to be identical. So for most functions and most spots on a graph, this criteria is going to be met. However, I've given one particular example here, which is as you come from the left-hand side, you reach the white circle. As you come from the right-hand side, you also reach the white circle. So the limit exists at that spot. It is defined at that spot because there's a vertical sliver, there's a dark circle floating above in that exact same spot. But this is not the same y value as this. And so for that reason, third criteria. The third criteria I don't believe shows up in the Unit 1 and 2 book, and the Unit 3 and 4 book doesn't even touch on limits at all and continuity. So that's merely only there just to cover your bases in case you get a really weird one. Hence the reason why I had to sort of draw this in, I think, MS Paint, perhaps. This is clearly an older document, which I didn't put on the... Well, no, I think this is the only way I could actually do it, because the other graphing tools don't really give you these white circle options. Anyway. Oh yeah, there's differentiability. Cool. So I guess before that, anything in there to clarify?
All good.
Sweet. Lastly, differentiability. So, basically put, like there's a whole thing you could read into, like basically this has to exist, but fundamentally as far as methods is concerned, you just want your original function to be continuous and the derivative of that function to also be continuous. If those are both continuous for all x, then it's differentiable for all x. Anytime there's a mismatch there, the function is considered non-differentiable at that spot. So technically speaking, all the criteria that we talked about here need to exist both on the original and the derivative function. But as a bit of a shortcut, pretty much what you can do is make use of your own understanding of the functions ahead of time. Like we know, quadratics, unless they've got a restriction on their domain, quadratics are always continuous. Same thing for linear, fully continuous. None of those functions have anything weird. Tan, for instance, does have asymptotes. Logarithms, also asymptotes. So depending on the functions you have in the piecewise, and I'm pretty sure they only ever really use polynomials, if I'm not mistaken. Yeah, it's a whole bunch of, well, this isn't really a polynomial, I guess, but it's linear. They don't really give you anything too crazy to work with. So you can pretty much just assume off the bat that the only thing you have to actually check is the handover when these functions cross. And that's always going to be at, whatever this piecewise tells you it crosses over at. In this case, x equals 0. So as long as you can prove they share a y value at that spot, and they share a derivative value at that spot, you can say everything else is going to be continuous for both functions and therefore differentiable. As far as observing it, you want smoothness. So if you have a perfectly smooth join, you'll be able to identify that as differentiable. When you don't have a smooth join, you have this sharp, jagged edge, you can immediately, without doing any further investigation, know that these are going to be going to not have the same derivative value at that spot, and therefore are going to be non-differentiable. What that ends up looking like is white circles at the gap. So for instance, this one has an increasing gradient from x greater than 0. This one has a consistent gradient, but because it's got a sharp, are we able to see it? We're not really able to see it. It'll be something like this. Like this has got some consistent positive gradient, this has got some consistent negative gradient. We don't know which one's which here, so we just draw a white circle on both if we're drawing our derivative graph. Hence is why you get this. And then there's just some notation stuff for the calves. Easy. All right, that's all the content for today, basically. Do you want to work on any of this stuff, or do you want to go through your questions?
Could we go through my questions, please?
Certainly can. All right, so I've got them all still written here. Curious how you went through that. Did you see the text reply?
No, I didn't.
Okay, cool. Let's see. Yeah, I realized I only wrote the answers to these instead of what the actual question was. So let me. How can I display these? Were there any in particular you wanted to have a look at, or just like from start to finish, all of them?
Start to finish if you're okay with that.
Yeah, I'm fine with it. No one else is here, so you're not exactly taking up time. It's all good. How do I just want to be able to get it on the recording for reference, and also know what the question was. So I just got to pull them up. One moment. How do I? This might work. Okay, if I now change my screen share over to PNG, that should be fine. Okay, cool. We'll probably do it this way then. Okay, cool. So example 1, distribution of scores follows a normal distributions, plural. 30% of scores are less than 45, 30% of scores are greater than 55. Find mean and standard deviation. So basically, first things first is normal distribution. That should be fairly obvious. It tells you what probability type you have. The key things to watch out for the normal distribution is to identify whether you're trying to solve a probability or whether you're trying to solve a statistic. Statistics are always solved using the Z equation, which is what we have to do. Right? We have to find our mean and standard deviation. Probabilities are always solved using a CDF. Or technically, if you have to do a tech-free, you might be doing the approximation, 68, 95, 99% rule stuff. Now, my recommendation for all of these types of questions is to start with a picture. So they said that 30% of scores are less than 45. So that's what that left-hand side is all about. 30% of scores are less than 45. They said the exact same thing for 55. 30% are to the right of that. And then I just sort of filled this in just because adding it all up to 100 seemed like a decent idea. Cool so far?
Yeah.
Okay. Now, that gives us some information to work with. From there, find mean and standard deviation. That tells us Z's going to be important. Now, I will say there is a shortcut to solving this one. I won't really touch on it first. I'll touch on it afterwards. This will be helpful for like just a general purpose. Anytime you have statistics to solve, use Z. As for how you get Z, that comes from the standard normal. So you're essentially using the inverse normal function on the CAS to achieve whatever the equivalent Z values are at that spot. So for TI and SPI, you have to make sure all of those are left, which is why I've set the area to 0.3 for this one, and then 0.7 for that one. Mean 0, standard deviation at 1, always for standard normal. That's going to get you these values. Remind me what CAS you have?
I have Inspire.
Yeah, okay. So these all look exactly verbatim what you put in. Fair enough on that so far?
Yeah.
Cool. From there, sim equation. So you want to solve both mean and standard deviation. That's 2 variables, 2 unknowns. Oh, sorry, 2 variables, 2 equations, right? So you technically didn't need to do a second inverse normal. You can kind of use the symmetry of this. If you notice, they're both like the positive and negative of each other. That's because they were equidistant from the center. Right, 30% left, 30% right. They're equally spaced from the center. But anyway, you have your 2 equations. plug them both in, and then that's just a CAD simultaneous solve. When you do that, you're going to get mean of 50, standard deviation 9.5. Cool?
Yeah.
Okay. Now, I said there's a bit of a shortcut to work with. That was one of them, which is you only need to do this calculation once to find one of the z's, and then do the reflection of that to get the other. Now, the other property of the symmetry of this situation means that you can actually calculate your mean immediately by the midpoint of these two things. So you've got 45, which is 30% left. You've got 55, which is 30% right. Because they're equally spaced, 50 is the midpoint there, and mean is always the center. So technically you didn't need to do a full simultaneous for this. You just needed at least one of those z values and then solve for the rest, because the mean could have been calculated with midpoint. Make sense?
Yeah.
Yeah. That's a bit of a nuance on this particular question. Every other question goes this way. All right, next up, we got this one, which means new PNG. Wait, this one, what was actually being asked here? A bunch of CDFs. Oh, it opens up in a new PNG window. Awesome, they don't stack. Let's fix that. Okay, let's see. Again, normally distributed, mean of 72, standard deviation of 8. So we're told the key statistics already, and we want to find probabilities. So kind of like as I said at the beginning, you're doing a normal CDF to find any normal probabilities. Now, one of the key things we were told is, that's interesting actually. Use a probability of z being less than 1 is equal to 0.84 to find these. Was this supposed to be tech-free?
Yeah.
Oh, okay.
Because it's short answer.
Was the other one tech-free? Can't have been. Had to be decimal places.
Yeah. I don't know, it's confusing because sometimes they say you can't use it. It's just like a worksheet.
Yeah. There's no 40% rule for, because you're not going to get z equals 0.52 without a
Yeah, you
cas.
need a house.
Yeah, like this one I can see you could have, because like these are using the 68, 95, 99% rule stuff. You could do that. I didn't actually quite clock that as the case though. Yeah, interesting. Anyway, so even if you don't use the normal CDF version of this, then basically what you end up doing is probability x being greater than 80. You again draw your curve. So drawing a quick normal distribution, we're told the mean was 72. Standard deviation of 8. So 80 is effectively one standard deviation to the right, because 72 plus 8 gets you to 80. So we put in our 80. And so probability of x being greater than 80 means you just want to figure out what the approximate probability is, one standard deviation right. For that, the way I prefer to typically do things is start with knowing where my 50% mark is. So everything left of here is going to be 0.5. Then from there, because it's one standard deviation right, plus minus 1 is 68%. Therefore, yeah, okay. Therefore, 34% is going to be here, 0.34. And to add everything else up, you're going to get 16%. The reason I hesitated there was because they've actually made it a bit easier for you, because they've told you ahead of time that this whole thing is 0.84, because it's z less than or equal to 1, or less than or equal to 1, sorry, which is, one standard deviation, and left is 0.84, therefore the remaining is 0.16. So they did make it a bit easier than that, but still having a picture there is good. And this overall approach is nice when you don't have that information. Okay.
Yeah.
Cool. This will be the exact same thing. So in this case, we were told to figure out between 64 and 72. Between 64 and 72, well, 72 obviously being the middle, and 64, it's going to be what, 2 standard deviations? So -8, -8, yeah. Hang on. No, it's 1 standard deviation. Cool. And so you've got your 68% rule either side, which makes 34% for just that section of it. Fair enough.
Yeah.
Cool. And again, it could be CDF. I didn't realize when I was writing these it was a thing. And the last is the conditional probability. We know it's conditional probability because of the keyword given. And so for that reason, when you're going through doing that, you start with your conditional probability formula, which means you want the intersection of these two things, and you want to divide by whatever the conditional is on the right-hand side. That's that. Cool so far for those?
Yeah.
Okay. Now, do you know how to simplify that intersection into an actual probability to solve?
Do we do the number line?
Yeah, number line is a great idea. So if we come over here, we have the key things as 64 and 72. We have x less than 64 as one of the values. We have x less than 72 as the other. And so with those two things on a number line, what does my intersection simplify to?
X is smaller than 64.
Sure does. Yeah, that's the one. Cool. So we now know it's just x smaller than 64. So PR x less than 64 is the top, and then PR x less than 72 is the bottom. Now, just because they're in a fraction doesn't mean you do it any differently. It's still just going to be looking at this and being like, oh yeah, there's my 64. Oh yeah, there's my 72. All right, still using the same symmetries there. Maybe give that one a shot yourself. See if you can now, because you've done a couple of those now. What do you think? So, for instance, probability of being less than 64. What's that going to be on this?
Um, because when X is larger than 80, it's 0.16.
Yep.
Would it be 0.16 there too?
Sure will be. Yeah, equidistant. Nice. So that top is therefore 0.16. And then the bottom being less than 72. This one will probably be easier for you as well.
0.34.
Fully less than 72. So everything left of 72.
0.5.
0.5. Yeah, correct. So half of 0.16, 0.08. Yeah, that's that. Nice. Okay, next up. Looks like this one was very similar to another question you've already done. Let's pull that up. Find probability x greater than 5. Okay. Pop that on the screen share real quick. Yeah, cool. Okay, so again, we're told mean, but this time we're told variance. So variance obviously slightly different to standard deviation. And then z is a standard normal as per typical. Finding probability x being greater than 5. Yeah, not really much to say beyond the fact that you have to convert your variance into a standard deviation. If this one's also a short answer, I mean, it's probably x greater than 5. Like, I'll let you answer that. What do you think it's going to be?
Um,
I'm going to draw a picture if you need to for the bell curve.
yeah. I'm not too sure how to section it off.
How to section it off. Okay. What have you got so far written down?
I wrote 5 in the middle,
Yep.
and then I just went by threes. So I did 8, 11.
Oh, yeah, sure. So typically, if you have a look at what I do to section, or what I actually choose to write down, it's typically just bell curve, mean, and then any specific x values that come up in the thing. So yes, you know that standard deviation is 3 for this one, and sure, it's okay to have everything written down for all the plus, minus, 1, 2, and 3 standard deviations. It does make it a bit messy, or at least makes your things a bit big to work with, but it's fine to have it all there. Now, probability x being greater than 5 just means everything right of 5. What's that mean on your curve?
0.5.
There you go. Yeah.
Ah, okay.
Yeah. There was no it didn't have like a what would it be, 5, 6, 7, 8. There was no like x equals 8 or anything like that. Yeah. So no additional x value to look at. Now for the next one, bit tougher. So you've now got an x probability that's equal to a z probability. Um, and so basically the way to interpret this kind of question is to identify that the thing you're trying to solve for, b, is associated with the standard normal, which means you're looking for a z value, essentially. So even though it says b, you're looking for a z. Now, I've actually written this exact, it may not be the exact numbers, but very much so the overall structure of the question is already in the notes for the standard normal distribution stuff. Yeah, it's in there, but we'll reread it now. So the key things we have are mean was 5, standard deviation was 3. We have probability of x being greater than 7 is the same thing as probability of z being less than b. Okay, those are the key things we have. This is where having that normal distribution will be nice. So draw that bell curve out. We've got 5 in the middle. We've got 7, which is immediately over here. Now, notably, that's not actually one standard deviation's worth, so we can't quite use any of our approximations to help out. And so to depict x being greater than 7, you might draw a line like that. Now, this one, a bit more challenging, right? Probability of z less than b. You would need another distribution, and then you'd have to kind of guess where to put this. So kind of tough to draw one for this. You can do it. Like for instance, if I were to do it, I would draw it like so. Because I kind of know ahead of time I want it to be the exact same area as this. So if I draw it on the right hand side, it's going to be bigger than 50%. I have to draw it on the left hand side. If I had to draw two separate ones, this is how I would do it. I wouldn't really do this though. Is it fair enough at least how I've created both of these?
Yeah.
Okay. So instead of doing that, my first recommendation is going to be to make sure your inequalities are pointing in the right direction. You don't really want to be trying to jump through hoops to try and figure out an equivalence between z and x when especially they're both pointing in the different directions. So what you can do instead is try to flip this one, because this is the one that we know a lot about, into a less than sign instead of a greater than sign. How could we rewrite this same total area as a less than sign rather than a greater than sign? What could we do?
X is smaller than 5.
Almost. Well, x is smaller than 5 will be a 50%, which isn't going to quite cut it for because x equals 7 is shifted right of the mean, but it's very similar to that. You want to go less than or left because you're less than inequality. What value should be there instead though?
3.
3, yes, that's it. 2 to the right is the same as 2 to the left. And so we're going to put a 3 there. Nice. So this is the same as that. So basically, instead of saying x greater than 7 is equal to this, we now say x less than 3 is equal to that. And the reason why that matters is because now you can say this x value of 3 is the same as this z value b. So when you do your z equation, you can say z, your b value, is equal to x minus the mean divided by the standard deviation. Yeah. And then that's obviously just simplifiable. So looking at negative 2 on 3, which makes a decent amount of sense. Negative because you're on this side, and not quite one standard deviation because, well, this wasn't quite one standard deviation. Oh.
Yeah.
Yeah. So use this kind of approach always. First start by flipping the inequalities using a symmetry of right to left. Typically you do the one that has the most information attached to it. This one you have basically everything you could want, so flipping this is easier. Flipping that a bit harder because you're kind of just floating b in a spot. Yeah, that's that one. And next picture. This is continuous, and this time it's definitely CAS. It's a multi. Okay, let's pull this up. Okay, continuous random variable, cosine over 3 pi over 4, 5 pi over 4, value of a equals a certain probability. So what's going on here with continuous is I'll give you a similar thing to how you do normal. So I said normal, when you're finding statistics, you use Z, and for probabilities using CDF. Similar thing can be said for continuous, which is when you're trying to solve probabilities, you use integrals. When you try to, well, okay, maybe that's a bit of a bad analogy because technically both are going to be integrals. When you try to solve probabilities, the integral is fully known and you're just solving the integral. When you're trying to solve specific x values, so you can see it's x or less than a, it's a specific x value, you're still using integrals, but you know the value ahead of time. What you don't know is either the upper or the lower bound of that integral. So if we're trying to find x less than a, is a an upper bound or a lower bound in this situation?
A would be upper.
A would be upper, absolutely. So the thing we don't know for our integral is the upper bound. So you would say integral from a to 3 pi over 4 of your cosine is equal to 0.25. Cas solve. So let's do exactly that. See what happens.
It's just that whenever I put on the CAS, it doesn't work.
Okay. Well, let's do it. So menu 3.1, get a solve going. We want to have, well, maybe check, do you have radians or degrees?
It's radians.
Okay. That's good. Okay, so 3 pi over 4 to a. Oh, when you say it doesn't work, do you get like a general solution?
Yeah.
Yeah, okay. All you got to do is put a domain on a between 3 pi over 4 and 5 pi over 4.
Oh.
Yeah, because general solution will always appear for any circular function thing. The thing you can always do to avoid that is put a domain on your function, or just go ahead and sub in different n values until you get one that fits. Either of those works. Do 5 comma a. As you see, you get a bunch of these. As I said, one way of doing that is domain. The other is you could even just come through here if you prefer, chuck a bunch of n equals 0, see if you get a value on the thing. If not, that's fine. Do it again for n equals 1, and eventually you'll find a value that you want. Depends on what's less painful to work with. And so part C, or answer C, should be correct there. 2.87 rounds to 2.88. Yeah. Fair enough.
Yeah, thank you.
No worries. Flying. Okay, that's that. So we finish that one. Next up. Oh, I just realized I can click the arrow keys to see the next. I don't have to jump in and out of the chat. Oh yeah, question 8's not in the study design. But I will talk about it just a little bit, just so you can have maybe a bit of an.
Yes, before we move on, how would you put the domain on the previous question?
Yeah, sure. Same thing you do for any solve, which is, now you got to remember, don't put it on x because x will disappear. You put it on a. So you go, what was it, 3 pi over 4 to 5 pi over 4, something like that. X less than, was it equal to? I guess it won't really matter. It was less than 5 pi over 4. Oh, that also gives you a bad answer. Huh. Yeah, okay. I guess you kind of do have to default to subbing in your n values there. I mean, you can slowly tighten this up, I guess. Like you can make it maybe 4 pi over 4, and eventually... Is it going to ever do it? No, okay. I guess you do just have to sub in your n values. That's the only thing you can do. Usually that works. Usually that'll, as long as your domain is sufficiently small or narrow, you typically don't get general solutions, but I guess in this case we still do. Odd.
What n values would we put in?
No, just what I was doing, starting at 0 and then working your way up. If you're
Oh.
clearly way too far off, like if this was saying like negative hundreds, it'd be like, okay, we need to choose a massively big n value, otherwise we're not going to get anywhere near the ones that we need. So yeah, there's a bit of guess and check going on in there, but in this case we just did n equals 0, n equals 1, and we got there. Cool.
Yeah.
Next up, did I download question 8? I did. Oh, right, I've already opened it. Okay, so this isn't part of the study design specifically because of this 3 minus x in modulus bars. So have you come across those absolute value bars before?
No.
Okay, I only briefly touch on it because you technically don't need to know it, but if you do see it in those older exam questions, basically what that means is if your function would become negative, make it positive instead. So typical 3 minus x is going to look like this, y-intercept of 3. It's going to have this section where it goes negative. Basically, any negatives immediately bounce back to being positives. So you just ignore that entire, you ignore all of this, and whatever the equivalent positive is bounces back up. And so that's what that's supposed to be. As for now how to find those probabilities, I mean the rest of it's now just sort of whatever, because now you have the function. You know, for less than 3.5, you're going to be looking at, I guess it'd be something like area from here to here. Actually, where is it? From 2 to 4. So you'll be looking at, zoom all the way in on that. You'll be looking at from here to here-ish. And that's just either integrals or even triangles if you want to do that. Either way, you're still just doing area under the curve. Cool?
Yep.
Okay. And then that backslash, I'm assuming, is a given sign. I feel like the teacher just sort of did a few typos there. I know your teachers type these out manually because the PRs are in italics and they haven't just been copied. But anyway, that's that one. Next download coming. Oh, that's why I had a different prefix, because there's 2 question 8s. Third. Okay. Cool. So, continuous random variable. Oh, nope. That's a bit weird. They call it continuous and also made it normal, which is technically correct. Normal distribution is continuous. Has that always? Maybe that has always been there. Anyway, we're told our mean and standard deviation, so we know it's probably not going to be a z thing. No, I lied. There's z immediately after. Maybe I should have read more than a single line. Probability z between -2 and 1 is equal to one of these distributions. Cool. Okay, so z being between -2 and 1, one of the first things you're probably going to identify from that is that the z equation is going to be appropriate here. If you look at all the possible answers, they're all in terms of x, except for part E, which is a bit weird, but technically is still in terms of x. But anyway, so to get things in terms of x from z, you're obviously using the z equation to get there. These ones don't require too much effort. This can just be solved tech-free. X equals 8, x equals 26, just by simply sewing in the known values that we have so far. So instead of saying z between -2 and 1, we can now say x between 8 and 26. Cool so far?
Yeah.
Problem is, that's not on the list. And so one of the things we have to do is now look at the symmetry of what's going on. Now, this is tech active, it's a multi-choice, at least I would hope so. And so one of the things you can do is actually just sort of CAS solve, hey, what is my probability between 8 and 26? Turns out to be 0.819. And so as long as you sort of ballpark it and figure out, yeah, this one looks roughly like a symmetry thing, you can just test that probability in a normal CDF and then see if they're equal to each other. That's a very guess and check approach where you just plug in answers A through E and then see which one matches the one that you got. The other approach would be to really hone in on what the symmetry is. Like for instance, from 8 to 20, if it's standard deviation 6, then you've gone from mean of 20 down to one left is getting you 14, another left is getting you 8. So it's 2 standard deviations left, 1 standard deviation right. You technically already know this because of the z. That already tells you it. And so basically, if you think about how you could be shifting these things, but basically you want to mirror this. So instead of going 2 left, 1 right, you go 1 left, 2 right. And that turns out to actually be on the list. The 14 and the 32 is one of the potential answers, specifically answer B. Cool with that?
Yeah.
Okay. Last one up, I think. Oh, last two up. Last photo. Let's get it. Yeah, there we go. Okay. Um, I'm not going to say anything about question 10. We've done it before today. I'll let you have a think now. See if you can use what you've learned.
Can we use the inverse normal?
Sounds like a great idea. Yeah, inverse normal. We don't know one of the x values, so inverse normal does give us x values. Nice. That'll be good. Only question now is what do we put in the area column? Do we put 0.2 or do we put something else? Under what circumstances should we flip that?
I'm not sure.
Not sure. Did you draw a graph of it?
Yeah.
Okay. What does your graph look like if you were to describe it?
It has a 30 in the middle,
Yep,
and then that's it.
that's it. Okay. If you were to draw a probability on there, so x being greater than a is equal to 0.2, how would you start depicting that on the graph?
On the left side, I would go A and then shade 0.2.
A, and then 0.2 in what direction, right or left?
Right.
Right. How's that look?
Not right.
Okay. What are we going to do to fix it?
Would the A go on the right side?
That looks a lot better to me. Yeah. There we go. Much better. So you can see just by drawing a graph, you can know pretty obviously, like, okay, I've done something wrong here. 0.2 is not going to be on that side, so let's just fix it up. And you probably didn't need me to say anything there. You would have drawn it and realized, okay, something's off. But yeah, everything else was good about that. You saw a greater than sign, so you know it's right, and you saw the probability, so you know you label it with that thing. It was just a matter of putting it on the correct side of the mean. Cool. All right, that's that picture. Now, with that in mind, we know we have to use an inverse normal. How do we put that in our TI Inspire CAS?
Um, the mean would be 30, and then the standard deviation would be 5.
Yep.
And
Just
then the error, yeah,
yeah, those are good. And then the area. Might have cut
would,
out there.
would
Test
it
it.
be 0.8?
0.8. Yes, because our CAS can only go left. Yeah. So you're just going to put 0.8 in there, which that's going to get you this 34.21, which of course is going to be D. Cool.
Yeah.
Yeah. I actually figured out. So the Casio has a center function, which means like if you're told a a probability between like here and here is like 0.4, for instance, you can choose center 0.4 and it'll tell you whatever this value is. It's kind of cool. It's the one thing that Casio does better than TI Inspire. But anyway, we're almost done here, so I guess I'll just sort of lecture this one a little bit. It'll run a little bit over time, but I'm sure you'll appreciate it nonetheless. So, question 11. Bit different, this one. So you're actually told what appear to be binomial features of it. You're told number of apple trees, and you're told that 1,735 of them have a height greater than 2.8. The thing you got to recognize is that you're told the heights are normally distributed. So you've got to sort of resist the urge to do binomial things to calculate it, and then go straight off of normal instead. So, because we're using normal, we know that we're trying to solve the mean. So, what did I say about when we have to solve a mean for normal? What's the typical thing?
We need to use the Z to find the statistic.
Yeah, using a Z, absolutely. So, we're going to be using the Z equation. We don't know the mean. We do know the standard deviation. And that's actually it. That's the things we know off rip. Now, what we can do is use the binomial looking stuff to actually calculate the probability of being greater than 2.8 meters. So, 1,735 out of a total 2,000 is your probability of being greater than 2.8 meters. That's what I've done as the very first statement there. So that actually gives us an x value and a probability associated with it. So we have x, we have standard deviation. We don't have mean. We could have z. We can pretty much always guarantee z as long as we have, well, yeah, we can pretty much always guarantee a z. And so, we have probability of x being greater than 2.8, which on a graph means, well, it's 0.86, so it's going to be a big one. You got your value and then everything right of that. So to get our z, as we saw before, we need to go left instead. So it's going to be 1 minus this is the area that we put on there. Since it's standard, mean of 0, standard deviation of 1, that's going to get you a z value of negative 1.11. You now have z, you have x, you have standard deviation. Cas solve out for the mean. Finished. How's that?
Yes, thank you so much.
No worries at all. You've obviously got copies of these in the text chat. This video will come out at some point as well, maybe within a day or so. So you've got that as well if you wanted to revise the reasons why behind it. Otherwise, yeah, I'll leave you to enjoy the rest of your day.
Thank you so much.
No worries. Happy to help.